The Earth moves through space at nearly 70,000 miles per hour, which means the hospital room where you first drew breath, that precise pocket of air, that exact location in the cosmos, now drifts somewhere far beyond the orbit of Mars, scattered into the cold and silent void where no one will ever stand again. There is something both melancholy and strangely freeing in this thought. The way it loosens our grip on the idea of return, the way it invites us to understand that home was never truly a place at all, but rather a moment, a feeling, a collection of sensations that traveled forward with us even as the universe carried the coordinates away. If these quiet reflections bring some ease to the restless hours, perhaps consider staying close for future journeys through the gentle dark. The stars have moved, the planets have turned, and so the telling begins. In 1940, the American novelist Thomas Wolfe published a book with a title that has since become something of a proverb, a phrase that people use even when they have never read the novel itself. The book was called You Can't Go Home Again, and it told the story of a writer who returns to his small hometown in North Carolina after achieving some measure of literary success, only to find that the place he remembered no longer exists in the way he remembered it. The people have changed. The buildings have changed. The feeling of the town has shifted in subtle ways that he cannot quite name. Wolfe was writing about memory, of course, and about the passage of time, and about the way that we carry places inside us that exist only in the past tense. He was writing about the emotional impossibility of return, the way that childhood homes shrink when we visit them as adults, the way that familiar streets seem narrower, the way that the corner store has become a parking lot. These are the ordinary heartbreaks of growing older, the small griefs that accumulate as the years pass and the world refuses to hold still for us. What Wolfe could not have known, or perhaps did not think to mention, is that his metaphor extends far beyond the emotional realm. There is a deeper truth buried in his title, a truth that has nothing to do with memory or nostalgia or the passage of human time. The place you were born, the actual physical location in space where your mother held you for the first time, where you drew your first breath and opened your eyes to a blur of light and shadow. That place no longer exists, not in any meaningful sense. The room may still be standing. The hospital may still bear the same name. The street outside may still be lined with the same species of trees. But the location in the universe where all of this happened, the precise coordinates in the vast emptiness of space where you came into being, that location is now millions upon millions of miles away, receding at tremendous speed, and you will never return to it. You cannot return to it. It is gone in the most absolute sense that anything can be gone. This is not a metaphor. This is not poetry. This is simply what happens when you live on a planet that moves. The instinct to return to our beginnings is one of the oldest and most persistent features of human consciousness. We feel drawn to the places where significant things happen to us, as though the walls and floors and ceilings of those places have absorbed something of our experience, as though by standing in the same room we might somehow reconnect with the person we used to be. Elderly people often speak of wanting to see their childhood home one more time. Adopted children sometimes feel a powerful need to visit the town where they were born, even if they have no memory of it, even if they lived there only for a few days. There is something in us that believes in the importance of physical return, in the meaningfulness of being present in a space where we were once present before. We plant trees on graves. We build monuments on battlefields. We preserve the houses where famous writers lived and died. And we walk through the rooms where they worked, looking at their desks and their bookshelves, as though the furniture might tell us something that the books themselves could not. This instinct, this deep and wordless pull toward the places of our origin, rests on an assumption so fundamental that we rarely think to examine it. The assumption is that places stay where they are. The assumption is that the hospital room where you were born is still in the same location it occupied on the day of your birth, waiting patiently for your return, fixed in place like a pin on a map. The assumption is that space itself is a kind of enormous container, static and unchanging, and that the objects within it, the planets and cities and buildings and rooms, occupy permanent positions within that container. This assumption feels so natural, so obviously true, that it hardly seems worth mentioning. Of course, the hospital is in the same place. Of course, the childhood home is still on the same street. Of course, the universe holds still while we move through it. But the universe does not hold still. The universe has never held still, and the ancient philosophers, those careful observers of nature who had nothing but their eyes and their minds to work with, understood this in their own way, long before we had telescopes or spacecraft or any means of measuring the motions of celestial bodies. Heraclitus was a philosopher who lived in the Greek city of Ephesus, on the coast of what is now Turkey, sometime around 500 years before the Common Era. Very little of his writing survives, only fragments quoted by later authors. But one of those fragments has echoed through the centuries and found its way into nearly every discussion of change and impermanence. Heraclitus observed that you cannot step into the same river twice. The idea seems simple enough on first hearing, almost obvious, the sort of thing that a child might notice while playing at the water's edge. The river flows. The water that was here a moment ago has moved downstream. The water that is here now will soon be somewhere else. If you step into the river, and then step out, and then step in again, you are stepping into different water. The river has the same name, occupies the same bed, flows between the same banks, but it is not the same river. It cannot be the same river. Sameness, Heraclitus seemed to be suggesting, is more complicated than we usually imagine. What Heraclitus understood about rivers, we must now understand about places, about rooms, about the very ground beneath our feet. The earth is not fixed. It never was. The sensation of stillness that we feel when we stand in a quiet room, the sense that we are stationary while the world holds steady around us, is a kind of illusion, a trick of perspective produced by the fact that everything nearby, the floor, the walls, the furniture, the air itself, is moving with us. We are all passengers on the same vessel, and because we cannot see the shore, we forget that we are moving at all. The ancient astronomer Claudius Ptolemy, who lived in Alexandria during the 2nd century of the Common Era, constructed an elaborate mathematical model of the heavens that placed the Earth at the absolute center of the universe, motionless and eternal, while the sun and moon and planets and stars revolved around it in complex patterns of circles upon circles. This model was not foolish. It was based on careful observation of the night sky. It made accurate predictions about the positions of celestial bodies. It matched what human beings actually experienced when they looked up at the stars. We do not feel the earth moving. We see the sun rise in the east and set in the west. We watch the stars wheel overhead in their stately procession. The most natural interpretation of these observations, the interpretation that any reasonable person would reach without additional information, is that we are standing still and the heavens are turning around us. Ptolemy's model endured for more than 1,000 years, until Copernicus and Kepler and Galileo assembled the evidence that the Earth is not the center of anything, that our planet is merely one of several worlds orbiting a rather ordinary star, that the apparent stillness of the ground beneath our feet is no evidence at all of actual stillness. The Earth moves. It spins on its axis once every 24 hours, so that a person standing on the equator is rotating at over 1,000 miles per hour, even while feeling perfectly stationary. And far more significantly, the Earth orbits the Sun, traveling in a vast elliptical path that takes 1 year to complete, so that by the time the calendar returns to your birthday, you have traveled in a circle nearly 600 million miles in circumference. To be precise, the Earth travels approximately 584 million miles per year in its journey around the Sun. This is such a large number that it becomes difficult to hold in the mind. It is easier to break it down into smaller pieces. The Earth travels about 1.6 million miles per day. By the time you have slept for 8 hours and woken to a new morning, you have moved about 530,000 miles through space without leaving your bed. By the time you finish a 1-hour meal, you have traveled about 67,000 miles. Every minute, whether you are walking or sitting or lying perfectly still, you move about 1,100 miles through space, carried along by the orbital motion of your planet. This means something for the room where you were born. That room exists. Let us imagine, in a hospital that is still standing, in a city that you could visit if you chose to, on a street that you could walk down any afternoon. The building materials are there. The walls and windows are there. Perhaps the bed has been replaced, but the floor is the same floor, and the ceiling is the same ceiling. And yet, the location in space where that room existed on the day of your birth, the actual coordinates in the universe where you took your first breath, that location is now inconceivably far away. If you were born 10 years ago, that location is now approximately 5.8 billion miles from where you are sitting. If you were born 40 years ago, it is more than 23 billion miles away. These distances place your birthplace well beyond the orbit of Neptune, out in the cold darkness of the outer solar system, in a region of empty space where no human being has ever traveled and where nothing at all exists. The room where you were born has traced an invisible spiral through the cosmos. This spiral is produced by the combination of two motions, the circular orbit of the Earth around the Sun and the linear motion of the Sun itself through the galaxy. The result is not a circle but a helix, a corkscrew path through space that never returns to the same point twice. Each year, as the Earth completes another orbit, it does so in a slightly different region of space than the year before, because the Sun has moved, carrying its family of planets along with it. The spiral stretches backward through time like the wake of a ship, marking every position that the Earth has occupied, and by extension, marking every position that you have occupied, from your first moment of life to this one. Even yesterday's location is unreachable. The place where you slept last night, the actual position in space where your bed existed while you dreamed, is now 1.6 million miles behind you. By cosmic standards, this is a small distance, almost negligible, but it is still far greater than any human being has ever traveled from Earth. The Moon is only about 240,000 miles away. The astronauts of the Apollo missions traveled farther from Earth than anyone before or since, and yet the distance they covered was less than a fifth of the distance that separates you from where you were sleeping just one night ago. This is the quiet astronomical truth that underlies Thomas Wolfe's literary observation. You cannot go home again, not only because the people have changed and the buildings have changed and your own memories have softened and shifted over the years, but because the home itself, the physical location in space where your home once existed, has been left behind in the endless forward motion of the Earth through the cosmos. The universe does not wait for us. It does not hold still so that we might return to the places we love. It carries us forward, moment by moment, mile by mile, into regions of space that no human eyes have ever seen. And it leaves the past scattered behind us like breadcrumbs on a path that we can never retrace. Let us begin, then, with something that feels so obvious it hardly seems worth mentioning. And yet, when you pause to consider it carefully, it becomes one of the most profound puzzles of human experience. The Earth beneath you, at this very moment, feels completely and utterly still. The floor does not tremble. The walls do not sway. If you were to set a glass of water on a table, the surface would remain as calm and flat as a mirror, betraying nothing of the tremendous velocities at which you are currently traveling through space. This sense of stillness is so complete, so convincing, so woven into every moment of your waking and sleeping life, that for most of human history it formed the foundation of our understanding of the cosmos itself. The Earth was still, and everything else moved around it, because that is precisely what our senses told us. And our senses, after all, were the only instruments we had. The ancient model of the universe, the one that placed our world at the center of all things with the sun and moon and stars wheeling about in crystal spheres, was not a foolish idea held by ignorant people. It was, in fact, a perfectly reasonable conclusion drawn from the available evidence, which consisted entirely of what human beings could see and feel and measure with the tools of their time. The stars rose and set with clockwork regularity. The sun traced its arc across the sky, and through all of this celestial motion, the ground remained reassuringly fixed beneath our feet. To suggest otherwise, to claim that the Earth itself was spinning like a top while simultaneously hurtling through space at tremendous speed, seemed not merely counterintuitive, but almost absurd. If we were moving so fast, the critics asked, why did we not feel it? Why did birds not get left behind when they took flight? Why did stones dropped from towers fall straight down rather than trailing behind as the Earth rushed away beneath them? These were not silly objections. They were serious scientific questions that required serious scientific answers, And those answers would not come fully formed until a Tuscan mathematician named Galileo Galilei sat down to write one of the most important books in the history of human thought. In 1632, Galileo published his dialogue concerning the two chief world systems, a work that would eventually land him in considerable trouble with the authorities, but which contained within its pages some of the most elegant reasoning about motion that had ever been committed to paper. The book takes the form of a conversation between three characters across several days. And while much of it deals with astronomical observations and mathematical arguments, there is one passage in particular that speaks directly to our question of why we cannot feel the motion of the Earth. Galileo asks his readers to imagine themselves below the deck of a large ship, shut away in a cabin with no windows, surrounded by various objects and perhaps some small flying creatures like butterflies or gnats. He describes how you might perform experiments in this enclosed space, dropping things, throwing balls, watching the flight of insects, observing water dripping from a bottle into a bowl below. When the ship is at rest in harbour, these activities proceed in a perfectly ordinary fashion. Drops fall straight down. Butterflies flutter about with equal ease in all directions. Tossed objects travel predictably through the air. Now, Galileo says, let the ship move at whatever speed you like, so long as the motion is uniform and not fluctuating this way and that. You will discover, he promises, not the least change in any of the effects described. The drops will still fall straight down. The butterflies will still fly without preference for any particular direction. You will not be able to tell, from any of these observations, whether the ship is moving or standing still. This thought experiment, simple as it may seem, contains within it one of the fundamental principles of physics: motion that is smooth and constant, what we would now call motion at uniform velocity, cannot be detected from within a closed system using mechanical experiments. There is no sensation that accompanies such motion, no force that pushes you toward the back of the cabin, no disturbance in the behavior of objects. Only when the motion changes, when the ship accelerates or decelerates, when it turns or rocks or rolls, do you become aware of movement. Galileo had identified something profound about the nature of motion itself, something that would later be refined and extended by Newton and eventually transformed by Einstein, but which remains true in its essential form to this day. The Earth, you see, is rather like Galileo's ship. It spins on its axis, carrying everything upon its surface along with it at considerable speed. If you happen to be standing somewhere along the equator, that broad belt that circles the planet at its widest point, you are at this moment traveling eastward at approximately 1,037 miles per hour, which is to say roughly 1,670 kilometers per hour for those who prefer metric measurements. This is faster than the speed of sound in air at sea level, a fact that might seem alarming if you pause to think about it, though of course there is no cause for alarm because you have been traveling at this speed your entire life without the slightest inconvenience. As you move away from the equator toward either pole, this rotational speed decreases because you are tracing a smaller circle with each turn of the planet. At the poles themselves, at those points where the axis of rotation meets the surface, you would merely be turning in place, like someone standing on a very slowly spinning platform, completing one full rotation every 24 hours. But rotation is only part of the story. The Earth also orbits the Sun, traveling along its elliptical path at an average speed of about 67,000 miles per hour, which is roughly 30 kilometers every single second. And the Sun itself is not stationary, but moves through the galaxy, carrying its family of planets along with it, while the galaxy itself drifts through the larger structures of the universe. All of this motion is happening right now, as you lie still in your bed, and yet you feel none of it because all of it is smooth. All of it is constant, and your body has no way of detecting such motion directly. The story of how humanity came to understand that space and time are intertwined in ways we cannot directly perceive begins, perhaps unexpectedly, with the moons of Jupiter. In 1676, a Danish astronomer named Ole Rømer was working at the Royal Observatory in Paris, carefully recording the times at which Io, the innermost of Jupiter's 4 large moons, disappeared behind its giant parent planet. These eclipses occurred with great regularity, and by tracking them over many months, astronomers hoped to create accurate tables that could be used for navigation and other practical purposes. But Rømer noticed something peculiar in his data. The timing of the eclipses seemed to vary depending on where Earth was in its orbit around the Sun. When Earth was closer to Jupiter, the eclipses appeared to happen earlier than predicted. When Earth was farther from Jupiter, they appeared to happen later. The discrepancy was not large, only about 22 minutes across the span of several months. But it was consistent, and it demanded explanation. Rømer proposed a remarkable hypothesis. Light, he suggested, did not travel instantaneously from place to place. It took time to cross the vast distances of space, and when Earth was farther from Jupiter, the light carrying news of the eclipse had to travel a longer path to reach us. This extra distance introduced a delay, which showed up as a timing error in the observations. Rømer's insight was nothing less than the first measurement of the speed of light, and although his calculated value was not perfectly accurate by modern standards, it was close enough to demonstrate the fundamental point. Light is not instantaneous. It travels at a finite speed, which means that when we look at distant objects in space, we are not seeing them as they are now, but as they were when the light left them. The sun you see in the sky is the sun as it appeared about 8 minutes ago. The stars are portraits painted years or centuries or millennia in the past. Space, it turns out, is full of time, and our perception of stillness is partly an illusion created by the vast scales involved. About 50 years after Rømer's discovery, an English astronomer named James Bradley set out to accomplish something that had eluded observers for centuries. He wanted to measure stellar parallax, the tiny shift in a star's apparent position that should occur as Earth moves from one side of its orbit to the other. Such a measurement would provide direct proof that Earth truly orbits the Sun, and it would also allow the distances to stars to be calculated for the first time. Bradley was a careful and patient observer, and he spent months tracking the position of a star called Gamma Draconis, which passed almost directly overhead from his location in England. He did indeed detect a shift in the star's position, but it was not the shift he had been looking for. Instead of the back and forth parallax motion, he found a small circular wobble that traced out over the course of the year in a way that did not match the predictions for parallax at all. After much puzzlement and careful analysis, Bradley realized that he had discovered something unexpected. The shift he was seeing was caused by the combination of Earth's orbital motion and the finite speed of light. Just as a person walking through falling rain must tilt their umbrella forward to stay dry, a telescope must be tilted very slightly in the direction of Earth's motion to catch the incoming light from a star. This effect, which Bradley called stellar aberration, provided the first direct observational proof that Earth truly moves through space. More than a century later, in 1851, a French physicist named Léon Foucault arranged a demonstration that would make the rotation of the Earth visible to anyone who cared to watch. He suspended a heavy iron ball from a wire 67 meters long, attaching it to the very top of the dome of the Panthéon in Paris. When set swinging, such a pendulum maintains its plane of oscillation relative to the fixed stars, because there is nothing to push it sideways, nothing to twist its path. But the building beneath it, and the city beneath that, and the Earth beneath all, are slowly rotating. As the hours pass, the floor of the Panthéon turns beneath the steadily swinging pendulum, and this rotation becomes visible as a slow drift in the pendulum's apparent direction. At the latitude of Paris, the plane of the pendulum completes a full rotation in about 32 hours. Crowds gathered to watch this simple demonstration, standing in hushed fascination as the heavy ball swung back and forth, its path slowly precessing around the compass rows marked on the floor. Here was proof of Earth's rotation that required no telescopes, no mathematical training, no faith in the reports of distant observers. The planet was turning, right there beneath their feet, and the pendulum was revealing it in real time. Foucault had made the invisible visible, had given people a way to see with their own eyes what their bodies could not feel. And this brings us, at last, to the question of why our bodies cannot feel these motions at all. The answer lies in the nature of our sensory systems, particularly in the delicate structures of the inner ear where our sense of balance resides. The vestibular system, as it is called, consists fluid-filled chambers and tubes lined with sensitive hair cells. When you move your head, the fluid sloshes against these cells, and the pattern of stimulation tells your brain which way you are turning or tilting. But here is the crucial point. The vestibular system detects acceleration, not velocity. It responds to changes in motion, not to motion itself. When you begin to move, the fluid in your inner ear lags behind momentarily, pressing against the hair cells and creating a sensation of motion. But once you reach a constant speed, the fluid catches up, settling into the same steady state as the rest of your body, and the sensation of motion fades away. This is why you feel an elevator begin to rise, but not the steady ascent that follows. It is why you notice a car accelerating, but can close your eyes and forget you are moving at all once the speedometer settles at a constant reading. Our biology is designed to alert us to changes that might require a response, not to waste its resources monitoring conditions that remain stable. And so the steady spin of the Earth, the unwavering orbit around the Sun, the smooth flow of the solar system through the galaxy, all pass beneath the threshold of perception. The Earth that seems still is, in truth, racing through space at speeds that would be terrifying if we could somehow perceive them. But we cannot perceive them, and so we do not find them terrifying at all. We find them, instead, restful, peaceful, conducive to sleep. The floor beneath you is solid. The walls around you are steady. The ceiling above you does not sway. And all of this stillness, this blessed calm, is a gentle conspiracy between the laws of physics and the design of your own body, a collaboration that allows you to rest easy in the midst of cosmic motion, drifting peacefully towards sleep on a world that never stops moving. When you picture Earth moving through space, it is natural to imagine our planet circling the Sun, tracing that familiar elliptical path that carries us through the seasons, through the years, through the quiet accumulation of time that makes up a life. And this image is true, as far as it goes. But it is rather like describing a person walking down the aisle of a train without mentioning that the train itself is hurtling across the countryside at considerable speed. The orbit of Earth around the Sun is real and important, but it represents only one layer of a much deeper motion, a motion that carries not just our planet, but our entire solar system on a journey so vast and so slow that it defies easy comprehension, and yet it proceeds all the same, moment by moment, carrying us somewhere we have never been before. The Sun, you see, is not fixed in space. It moves, and everything that belongs to it moves along with it, caught in the gentle, gravitational embrace that binds our cosmic family together. The planets, the moons, the asteroids tumbling quietly through the darkness, the comets drifting in from the frozen outer reaches, the spacecraft we have sent outward bearing messages to no one in particular, all of these travel with the Sun as it traces its own immense orbit around the center of our galaxy, the Milky Way. And when we measure this motion, when we calculate just how quickly our star is carrying us through the galactic neighborhood, the numbers become quite remarkable, though they are delivered here in the same calm tone one might use to report the weather. The solar system travels around the center of the Milky Way at approximately 514,000 miles per hour, which works out to roughly 828,000 kilometers per hour if you prefer that way of measuring things. This is a speed that the human mind cannot easily grasp through direct experience. As the fastest any person has ever traveled relative to Earth was the crew of Apollo 10, who reached about 25,000 miles per hour on their return from the Moon, a speed that felt quite dramatic at the time, but which is merely a small fraction of the pace at which we are all, always, traveling through the galaxy. And yet, you do not feel this motion, any more than you feel Earth spinning on its axis or circling the Sun, because everything around you, the air, the ground, the cup of tea growing cold on your nightstand, is moving along with you, and motion is only felt when it changes, not when it persists. The understanding that our Sun participates in this grand galactic rotation came gradually to human awareness, as most scientific insights do, through the patient accumulation of observations and the careful work of people who were willing to look at the universe and ask what it was actually doing, rather than what they expected it to do. In the year 1927, a Dutch astronomer named Jan Oort was working at the Leiden Observatory in the Netherlands, studying the motions of stars in our cosmic neighborhood. Oort was particularly interested in measuring the velocities of stars, determining not just where they appeared to be in the sky, but how quickly they were moving towards us or away from us, and whether their motions followed any discernible pattern. What Oort discovered, through meticulous analysis of stellar velocities, was that the stars of the Milky Way are not simply drifting about at random, but are participating in an organized rotation around a common center. Stars closer to the galactic center, he found, complete their orbits more quickly than stars farther out, a pattern called differential rotation. And by studying these velocity differences, Oort was able to confirm that our galaxy is indeed a rotating system, with the Sun and all its planets swept along in the flow. This was not the first suggestion that the Milky Way might rotate, but Oort's work provided the quantitative measurements that transformed speculation into established fact. And his analysis remains foundational to our understanding of galactic dynamics to this day. It is worth noting that Oort did this work when he was still quite young, only in his late 20s, and that he would go on to make many other contributions to astronomy. But this early achievement alone would have been enough to secure his place in the history of the science. Now, when we speak of the Sun orbiting the center of the galaxy, we must reckon with the scale of this orbit. And here, the numbers become so large that they slip past the mind's ability to hold them firmly. One complete journey around the Milky Way, which astronomers sometimes call a galactic year or a cosmic year, takes approximately 225 to 250 million Earth years to complete. This is a span of time so immense that it contains within it the rise and fall of entire branches of life on Earth, the reshaping of continents, the formation and erosion of mountain ranges, the coming and going of ice ages and warm periods and mass extinctions and slow recoveries. The last time the solar system occupied roughly this same position in its orbit around the galaxy, dinosaurs had not yet appeared on Earth. The Triassic period was only just beginning, and the dominant land animals were various reptiles and early relatives of mammals, none of whom could have looked up at the stars and wondered about their motion. Since Earth first formed, approximately 4.5 billion years ago, the solar system has completed somewhere around 20 of these galactic orbits, give or take a few, depending on how precisely one wishes to calculate. 20 journeys around the heart of the Milky Way, each one lasting longer than the entire history of complex life on Earth, each one carrying us through regions of space we will never visit again in any meaningful sense. The enormity of this is not meant to alarm you, but simply to provide a sense of context, a gentle reminder that the place you occupy in the universe is not a fixed address, but a momentary position along a path that stretches backward and forward through time spans that dwarf all human history, all recorded memory, all the stories we have ever told ourselves about who we are and where we came from. As our understanding of galactic rotation developed over the decades following Oort's work, astronomers began to make increasingly precise measurements of how galaxies spin, not just our own Milky Way, but other spiral galaxies scattered throughout the observable universe. And in the 1970s, an American astronomer named Vera Rubin, working at the Lowell Observatory in Arizona, made observations that would reshape our understanding of the cosmos in profound and unexpected ways. Rubin was studying the rotation curves of spiral galaxies. which is to say, she was measuring how quickly stars at different distances from the galactic center were orbiting around it. According to the expectations based on the visible matter in these galaxies, the stars in the outer regions should have been moving more slowly than those closer to the center. Much as the outer planets of our solar system orbit the Sun more slowly than the inner planets, because the gravitational pull weakens with distance from the central mass. But this is not what Rubin observed. Instead, she found that the rotation curves of spiral galaxies were remarkably flat, meaning that stars in the outer regions were moving just as quickly as stars closer to the center, as if there were far more mass present than the visible stars and gas could account for. This was deeply puzzling, because if you added up all the matter you could see, the light-emitting stars and glowing gas clouds, there simply was not enough of it to explain the gravitational pull required to keep those outer stars moving so swiftly without flying off into intergalactic space. The implication, which Rubin and her colleague Kent Ford explored carefully through observation after observation, was that galaxies must contain vast amounts of matter that does not emit or absorb light. Matter that makes its presence known only through its gravitational influence on the things we can see. This unseen substance came to be called dark matter. And while its precise nature remains one of the great open questions in physics, its existence is now widely accepted based on multiple independent lines of evidence, including the rotation curves that Rubin first studied so carefully. The Milky Way, like other spiral galaxies, appears to be embedded in a vast halo of dark matter that extends far beyond the visible disk of stars. And this dark matter shapes the gravitational landscape through which we travel, influencing our path in ways we cannot directly perceive but can infer through careful measurement. So when we speak of the solar system's journey through the galaxy, we must acknowledge that this journey is shaped not only by the stars and gas we can see, but by an invisible scaffolding of mass that surrounds and permeates the galaxy, guiding us along a path determined by forces we are still working to understand. The motion of the solar system through the Milky Way is not a simple flat circle, but rather a more complex trajectory that includes a gentle oscillation perpendicular to the galactic plane. Imagine the galaxy as a great flat disk of stars, gas, and dust, with most of the visible matter concentrated in a relatively thin layer extending outward from the central bulge. The Sun, as it orbits the galactic center, does not stay precisely within this plane, but bobs gently up and down through it, like a carousel horse rising and falling as it travels around the ride. This vertical oscillation has a period of approximately 30 million years, meaning that every 30 million years or so, the Sun crosses from one side of the galactic plane to the other, passing through regions of slightly higher density where stars and gas clouds are more concentrated. Some scientists have speculated about whether these passages through the galactic plane might have any influence on conditions here on Earth, perhaps by increasing the likelihood of gravitational perturbations that could send comets tumbling in from the outer solar system, or by exposing Earth to different radiation environments. These ideas remain speculative and are mentioned here only in passing, not to suggest any certainty, but simply to illustrate that our journey through the galaxy is not entirely abstract, that it connects, however tenuously, to the physical circumstances of our home planet. For the most part, however, this gentle bobbing motion proceeds without any noticeable consequence to us. One more layer of motion added to all the others, carrying us through space in a complex dance we rarely stop to consider. At present, the solar system is located approximately 26,000 light-years from the center of the Milky Way, positioned within a region called the Orion Arm, which is one of the smaller spiral arms branching off from the galaxy's more prominent structural features. The Orion Arm is sometimes called the Orion Spur or the local arm, and it lies between two larger arms, the Perseus Arm farther from the center and the Sagittarius Arm closer in. When you look up at the night sky and see the band of the Milky Way stretching across the darkness, you are looking along the plane of the galactic disk, seeing the accumulated light of billions of stars, too distant to resolve individually, but bright enough together to form that soft glowing path our ancestors named for spilled milk. We are not at the center of the galaxy, nor at its outer edge, but somewhere in between, in a relatively quiet neighborhood where conditions have been stable enough over billions of years for life to arise and persist and eventually develop the capacity to wonder about its cosmic address. The galactic center itself is a crowded and energetic place, home to a supermassive black hole millions of times more massive than the Sun, surrounded by dense star clusters and intense radiation fields that might make life as we know it difficult to sustain. Our position in the Orion Arm, far from that turbulent core, has perhaps been fortunate, though we cannot know for certain what alternatives might have allowed. And so the solar system continues its long, slow journey around the galaxy, carrying Earth and all its passengers through space at speeds we cannot feel and on timescales we cannot fully imagine. One more layer of motion in a universe that has never been still. And now we may add another layer to this gentle accumulation of motion, another current in the vast and quiet river that carries us through the cosmos. Because the Milky Way itself, this great spiral of stars that we call home, is not fixed in place but drifts steadily through the void, part of a larger pattern of movement that extends to the very edges of the observable universe. To understand this motion, we might turn our attention to a particular moment in the history of astronomy, a moment that took place on a mountain in California nearly a century ago, when a man named Edwin Hubble sat in the cold dome of the Mount Wilson Observatory and examined the faint smudges of light that had puzzled astronomers for generations. It was the year 1929, and Hubble had been studying what were then called spiral nebulae, those hazy patches in the night sky that seemed neither to be single stars nor clusters of stars, but something else entirely, something whose nature had been debated for decades. What Hubble discovered, through careful measurement of the light from these distant objects, was that nearly all of them appeared to be moving away from us. The light reaching his telescope showed a particular signature, a stretching of wavelengths toward the red end of the spectrum, and the degree of this stretching, this redshift as it came to be called, correlated with distance in a remarkably consistent way. The farther away a galaxy was, the faster it appeared to be receding from us, as though the entire universe were expanding outward in all directions, carrying galaxies apart from one another like raisins in a rising loaf of bread. This discovery, published in a paper that would become one of the most influential in the history of cosmology, revealed that we live in a universe that is not static but dynamic, not fixed but flowing. A universe in which the very fabric of space itself stretches and expands with the passage of time. And within this expanding universe, our Milky Way galaxy moves along with the flow, participating in the great cosmic drift that carries all things outward from the place where time and space began. But the motion of our galaxy is not simply a matter of being carried along by the expansion of the universe. There are also local currents, gravitational tugs and pulls from nearby collections of matter that give the Milky Way its own particular path through the void. To understand these local motions, we must first understand that our galaxy is not alone in its corner of the cosmos, but is part of a small family of galaxies bound together by the gentle but persistent force of gravity. This family is called the local group, a modest name for a modest collection of galaxies, numbering approximately 80 members in all, scattered across a region of space roughly 10 million light-years in diameter. Among these 80 galaxies, 3 stand out as the largest and most prominent, the giants around which the smaller members orbit and cluster. The first of these giants is, of course, our own Milky Way, a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars, depending on how one chooses to count and which estimates one prefers. The second giant is the Andromeda Galaxy, also known by its catalogue designation M311, a spiral galaxy somewhat larger than our own, containing perhaps 1 trillion stars and lying approximately 2.5 million light-years away in the direction of the constellation that gives it its name. And the third notable member is the Triangulum Galaxy, designated M33, a smaller spiral that lies about 3 million light-years distant and contains perhaps 40 billion stars, making it the third largest member of our little family. The remaining members of the local group are much smaller affairs: dwarf galaxies and irregular galaxies and small elliptical systems, many of them orbiting the larger members as satellites, bound by gravity into long, slow dances that will continue for billions of years. Some of these smaller galaxies are so faint and diffuse that they were only discovered in recent decades. Their dim collections of stars barely distinguishable from the background of the sky. What holds this family together? What prevents these 80 galaxies from simply drifting apart with the expansion of the universe? Is the gravitational attraction between them? Within the local group, gravity is strong enough to overcome the cosmic expansion, to bind these galaxies together into a unit that will remain coherent even as the rest of the universe continues to expand and recede. We are tied to Andromeda and Triangulum and all the rest, linked by invisible threads of gravitational force that will never break. And here we come to a rather remarkable fact, one that speaks to the dynamic nature of even seemingly eternal cosmic structures. Because the Milky Way and the Andromeda Galaxy are not merely drifting together with the general motion of the local group, but are actively approaching one another, moving closer with each passing moment, drawing together across the vast gulf of intergalactic space. The speed of this approach is considerable by human standards, roughly 250,000 miles per hour, or approximately 110 kilometers per second, a velocity that would carry you from the Earth to the Moon in about an hour. And yet, given the enormous distances involved, this speed translates into a very slow closing of the gap, a gradual diminishing of the 2.5 million light-years that currently separate us from Andromeda. The eventual outcome of this approach was first calculated with precision by an astronomer named Roland van der Marel and his colleagues at the Space Telescope Science Institute in Baltimore, who used careful measurements of the motion of stars within Andromeda to determine the galaxy's trajectory through space. Their calculations, refined over the years with increasingly precise data, indicated that the Milky Way and Andromeda are destined to collide, to merge together into a single larger galaxy in approximately 4.5 billion years from now. This calculation was further refined in 2019 with data from the Gaia Space Telescope, a European mission that has measured the positions and motions of more than 1 billion stars with unprecedented accuracy. The Gaia data confirmed the basic picture, showing that the collision is indeed coming, that the two great spirals of the local group are on a converging path that will eventually bring them together. When this collision occurs, in that unimaginably distant future, the result will not be the catastrophic crash that the word collision might suggest to human ears. The stars within each galaxy are so widely separated, so tiny compared to the vast emptiness between them, that very few, if any, will actually collide directly. Instead, the two galaxies will pass through one another, their stars mingling and mixing, their gravitational fields distorting and reshaping each other's structures over hundreds of millions of years, until eventually they settle into a new configuration, a single elliptical galaxy that astronomers have sometimes called Milkomeda or Milkdromeda, though of course there will be no one to call it anything at all, the Sun having long since exhausted its fuel and cooled to a fading ember. But let us return from that distant future to the present, where we may consider yet another layer of cosmic motion, one that was discovered not through the observation of galaxies, but through the study of something far older and far more subtle, the faint afterglow of the universe's birth itself. In 1977, a team of scientists, led by a physicist named George Smoot, made a discovery that revealed something unexpected about our motion through the cosmos. They were studying the cosmic microwave background radiation, that faint bath of radio waves that fills all of space, the cooled remnant of the intense light that filled the universe in its earliest moments, when matter and radiation were still coupled together in a hot, dense plasma. What Smoot and his colleagues found was that this microwave background radiation was not perfectly uniform across the sky. It appeared slightly hotter in one direction and slightly cooler in the opposite direction, a pattern called a dipole, as though we were moving through this bath of ancient light and encountering more of it in the direction of our motion, less of it in the direction from which we came. This dipole effect was caused by our motion relative to the cosmic microwave background, relative to the frame of reference in which the oldest light in the universe would appear perfectly uniform. By measuring the degree of this asymmetry, Smoot and his team could calculate our velocity, the speed at which we are moving through the sea of ancient photons that fills the cosmos. The result was rather surprising, for it indicated that we are moving quite rapidly indeed. Not just the Earth around the Sun, not just the Sun around the galaxy, not just the galaxy within the local group, but the entire local group as a whole all 80 of its member galaxies, moving together in a particular direction at a velocity of approximately 370 miles per second, or about 600 kilometers per second. This is a remarkable speed, more than 2 million miles per hour, carrying our entire galactic family through space at a pace that would take us from the Earth to the Sun in less than a day. And the direction of this motion, the heading toward which we are traveling, points toward a region of space in the direction of the constellations Centaurus and Hydra, toward something that has been given the rather evocative name of the Great Attractor. The Great Attractor was identified in 1986 by a team of 7 astronomers, led by Alan Dressler and sometimes called the Seven Samurai, in affectionate reference to the classic film. These 7 researchers had been studying the motions of galaxies in our cosmic neighborhood, mapping the flows and currents of galactic drift, when they noticed that a large number of galaxies, including our own local group, seemed to be streaming toward a particular region of space, as though drawn by some enormous but invisible concentration of mass. The mass required to produce this streaming motion was calculated to be enormous, equivalent to tens of thousands of galaxies, enough gravitational pull to influence the trajectories of everything within hundreds of millions of light years. And yet, when astronomers looked towards this region of space, they could not see what was doing the pulling. The pulling could not observe the great concentration of matter that must be producing this effect. The reason for this invisibility lies in an unfortunate accident of cosmic geography, for the Great Attractor lies behind a region of sky called the Zone of Avoidance, a broad band across the heavens where the dust and stars of our own Milky Way's disk block our view of the universe beyond. Looking toward the Great Attractor is like trying to look through a dense forest, the trees and undergrowth obscuring whatever lies on the other side. In the years since its discovery, astronomers have worked to peer through this zone of obscuration using wavelengths of light that can penetrate the dust more readily, infrared and radio waves that pass through where visible light is blocked. These observations have revealed that the Great Attractor is not a single object, but a vast concentration of galaxy clusters, a region of space where matter has gathered more densely than average, creating a gravitational well toward which surrounding material flows. But even the Great Attractor is not the final word in this cascade of cosmic motion, for it too is falling toward larger concentrations of matter still further away, participating in flows and currents that extend to ever larger scales, until eventually one reaches the scale at which the universe appears uniform, where the local variations average out and the only motion remaining is the general expansion of space itself. And so we drift, our galaxy and its companions, through the quiet darkness of intergalactic space, pulled gently by the gravity of matter. We cannot see, part of a cosmic flow that has been underway for billions of years and will continue for billions more. The motion is imperceptible to us, too slow and too vast to register on any human timescale, and yet it is carrying us steadily onward, away from where we were and towards where we will be, never returning to the same place twice in this universe of ceaseless and gentle motion. To understand just how far we have traveled from any point we might call home, astronomers have had to develop remarkably clever methods for measuring motion that cannot be directly observed. You cannot, after all, Watch a galaxy drift across the sky in the way you might watch a bird cross your field of vision. The timescales are far too vast, too vast. The distances too immense. And so researchers have had to find other ways of detecting these invisible rivers of motion that carry everything, ourselves included, through the cosmos. The story of how they learn to map these currents is itself a gentle and fascinating journey, one that has unfolded over decades of patient observation and careful thought. And it has revealed that we are embedded in flows of matter so large that they dwarf anything we might have imagined. The work of cataloguing these cosmic motions has been led in large part by a project known simply as Cosmic Flows, an ongoing collaboration that began in earnest in the early years of this century and has continued to grow ever since. At the heart of this effort is Brent Tully, an astronomer based at the University of Hawaii who has spent much of his career studying the large-scale structure of the universe and the movements of galaxies within it. Tully and his colleagues have assembled measurements of what are called peculiar velocities for more than 18,000 galaxies, a painstaking collection of data that represents one of the most comprehensive maps of cosmic motion ever constructed. Each of these peculiar velocities tells us something about how a given galaxy is moving relative to the smooth expansion of the universe. And when you gather enough of them together, patterns begin to emerge. Patterns that reveal the underlying currents and flows that shape the distribution of matter on the largest scales. To understand what a peculiar velocity actually is, it helps to think first about the more familiar motion caused by the expansion of space itself. As we discussed earlier, the universe is stretching, and this stretching carries galaxies away from one another at speeds that depend on how far apart they are. This component of a galaxy's motion is called the Hubble flow, named after Edwin Hubble, who first demonstrated that more distant galaxies recede from us more quickly than nearby ones. If the universe were perfectly smooth and uniform, the Hubble flow would be the only motion we would observe, and every galaxy would simply be drifting away from every other galaxy at a rate determined solely by its distance. But the universe is not perfectly smooth. It is lumpy and textured, filled with concentrations of matter here and relative emptiness there. And these irregularities create gravitational tugs that pull galaxies this way and that, adding an extra component to their motion on top of the steady recession caused by cosmic expansion. This extra component is the peculiar velocity, and it represents the motion of a galaxy through space rather than with space. A galaxy might be receding from us due to the expansion of the universe at a certain rate. But if there is a massive concentration of matter off to one side, the galaxy will also be pulled in that direction, and its observed velocity will be the combination of both effects. By carefully measuring the total velocity of many galaxies and then subtracting the component expected from the Hubble flow, astronomers can isolate these peculiar velocities and begin to build a picture of the gravitational landscape that causes them. It is rather like measuring the speed of leaves floating down a river and noticing that some are moving faster or slower than the current would suggest. Perhaps because they are caught in eddies or drawn toward the banks by subtle variations in the flow. The Cosmic Flows project has refined these measurements over several iterations, each one incorporating more galaxies and more precise distance estimates than the last. Determining distances to galaxies is itself a challenging endeavor. one that relies on a variety of techniques, including observations of certain types of variable stars, the brightness of supernova explosions, and correlations between the rotation speeds of spiral galaxies and their intrinsic luminosity. Each method has its own sources of uncertainty, and combining them requires considerable care. But the result has been a steadily improving map of peculiar velocities across an ever larger volume of the cosmos. These maps have revealed that galaxies are not simply scattering outward from the Big Bang in random directions, but are instead streaming along coherent paths, drawn by gravity toward regions where matter is concentrated and away from regions where it is sparse. One of the most significant discoveries to emerge from this work came in the year 2014, when Brent Tully, together with the French astrophysicist Hélène Courtois and their collaborators, published a study that redefined our understanding of where we live in the cosmic structure. Using the velocity flow maps constructed from cosmic flows data, they identified a vast basin of gravitational attraction that they named Laniakea, a word drawn from the Hawaiian language meaning immense heaven. This was not simply a cluster of galaxies or even a collection of clusters, but something larger still, a supercluster that encompasses roughly 100,000 galaxies spread across a region of space some 520 million light-years in diameter. Our own Milky Way, along with the local group, the Virgo cluster, and many other familiar structures, all lie within Laniakea, all of them caught up in a common flow toward a region of concentrated mass known as the Great Attractor. The discovery of Laniakea was made possible by a new way of thinking about the boundaries of superclusters. Rather than defining them simply by the distribution of galaxies in space, Tully and Courtois defined them by the patterns of motion, by the way galaxies flow toward certain regions and away from others. In this view, a supercluster is something like a watershed, a region within which all matter is flowing toward a common center, just as all water within a river basin eventually finds its way to a single outlet. The boundaries of Laniakea are not walls or edges in any physical sense, but rather dividing lines where the direction of flow changes, where galaxies begin to fall toward a different attractor belonging to a neighboring supercluster. It is a beautifully intuitive way of carving up the cosmos, one that respects the actual motions of matter rather than imposing arbitrary divisions. The visualization of Laniakea and the surrounding structures was greatly aided by the work of Daniel Pomarède, a French astrophysicist who specializes in creating three-dimensional representations of cosmic data. His animations and renderings have allowed researchers and the public alike to see the flow fields that define these superclusters, to watch as streamlines trace the paths that galaxies follow under the influence of gravity. These visualizations reveal a universe that is far from static, a place where matter is constantly in motion, sliding along invisible contours toward the densest regions and streaming away from the emptiest ones. The effect is rather like watching time-lapse footage of clouds forming and dissipating, except that the timescales involved are measured in hundreds of millions of years, and the clouds are made of galaxies. Beyond Laniakea, there are even larger structures that influence our motion through space. The Shapley supercluster, located roughly 650 million light-years away in the direction of the constellation Centaurus, is one of the most massive concentrations of matter in the nearby universe, and its gravitational pull reaches across the void to tug at us even now. The Shapley supercluster is so dense and so extensive that it contributes significantly to the peculiar velocity of our own galaxy, adding to the pull of the Great Attractor and drawing us in a direction that astronomers have spent decades trying to understand. For a long time, the motion of the Milky Way and its neighbors seemed difficult to explain by the visible matter alone, and this led to the suspicion that there must be additional structures, either attracting us from ahead or pushing us from behind, that had not yet been identified. In the year 2017, a team led by the Israeli astrophysicist Yehuda Hoffman announced a discovery that filled in part of this puzzle. Using the same peculiar velocity data from cosmic flows, they identified a region of space that appeared to be remarkably underdense, a great void containing far fewer galaxies than the cosmic average. This region, which they called the dipole repeller, lies in the opposite direction from the Shapley supercluster, and its relative emptiness means that it exerts less gravitational pull on us than the denser regions do. The effect is something like being caught between two forces, with the massive attractors ahead of us pulling us forward and the empty void behind us effectively pushing us in the same direction by failing to pull us back. The term repeller is perhaps a slight misnomer, since gravity is always attractive and voids do not actually push anything. But the net result is the same as if we were being propelled from behind while being drawn from ahead. The dipole repeller helps to explain why our motion through space is so substantial, why the Milky Way and its companions are streaming at roughly 600 kilometers per second relative to the cosmic microwave background radiation. This is not a gentle drift, but a significant velocity, one that carries us some 20 million kilometers every hour, though of course we feel nothing of it. The combined influence of the Great Attractor, the Shapley supercluster, and the dipole repeller creates a gravitational landscape that shapes our trajectory. And this landscape itself is shifting and evolving as the universe expands and matter continues to flow and concentrate over billions of years. We are caught in cosmic currents that we only recently learned to see, currents that have been carrying us along since long before our planet formed and will continue to do so for eons after we are gone. The methods used to map these flows have grown increasingly sophisticated over the years. Early estimates of peculiar velocities were based on relatively small samples of galaxies with considerable uncertainties in their distances, and the resulting maps were correspondingly crude. But as the sample sizes have grown and the distance measurements have improved, the picture has become steadily clearer. The most recent iterations of the Cosmic Flows project have incorporated data from space telescopes and large ground-based surveys, extending the reach of the maps and refining the details of the flow fields. There is still much that remains uncertain, particularly at the greatest distances where individual galaxy measurements become difficult and the effects of noise and systematic errors become more pronounced. But the broad outlines of the cosmic currents are now well established. What these maps reveal is a universe in constant, quiet motion, a place where nothing stands still and where the concept of a fixed location has no real meaning. The invisible rivers of gravitational flow are not chaotic or random, but follow predictable paths determined by the distribution of matter. paths that astronomers can now trace and visualize with remarkable precision. To look at one of Pomered's animations is to see the universe as it actually behaves, not as a frozen tableau of distant points of light, but as a dynamic, interconnected web of motion and influence. Every galaxy is simultaneously being carried outward by the expansion of space and pulled sideways by the gravitational tug of its neighbors. And the combination of these effects produces a complex dance that unfolds over timescales far beyond human comprehension. And so, as you rest your eyes and let these thoughts settle gently in your mind, you might consider that the place you were born has been carried along by these same currents, that the Earth and the Sun and all the stars you can see have been drifting through the cosmic flow ever since they formed. The invisible rivers of motion discovered by Telly and Courtois and their colleagues are not merely abstract features of distant space, but are the very currents that have shaped your own journey, carrying you across hundreds of millions of kilometers with every passing year. We are all passengers on this slow voyage, traveling together through the immense heaven of Laniakea, drawn by attractors and nudged by voids, part of a cosmic circulation that we have only just begun to map and understand. Let us now consider something rather personal, which is the matter of calculating where exactly you came into the world, and what has become of that location in the years since. This is the kind of arithmetic that sounds at first as though it might be unsettling, but which becomes, when we work through it slowly together, simply another gentle fact about the universe in which you have always lived. The mathematics here are not difficult. Really, just a matter of adding velocities and multiplying by time, though the numbers themselves grow rather large in a way that invites us to pause and breathe and let them settle into our understanding like sediment drifting to the bottom of a still pond. If you were born 30 years ago, which is to say roughly 10,950 days past, give or take a little, depending on leap years and the precise timing of your arrival, then you have traveled an almost incomprehensible distance from the coordinates of your birth. The figure works out to approximately 49 billion miles. Though this is an estimate that depends on which motions we choose to include and which reference frame we select as our standard, and, as we shall discuss shortly, the choice of reference frame is not so straightforward as one might hope. Still, 49 billion miles is a reasonable approximation, and it is worth taking a moment to consider how we arrive at such a number, because the calculation itself is rather soothing in its methodical progression from one velocity to the next. We begin with the motion you know best, which is the Earth's patient orbit around the Sun. Our planet travels through space at approximately 67,000 miles per hour, which sounds terribly fast when stated plainly, but which we experience as perfect stillness. Lying here, as you are now, with no sense of motion whatsoever. The Earth completes one full orbit each year, tracing out an ellipse that is very nearly circular, with a circumference of about 584 million miles. Over 30 years, this orbital motion alone carries you roughly 584 million miles times 30, which is to say about 17.5 billion miles. Though of course you return to approximately the same position relative to the Sun each year, like a very slow and very large carousel. The orbital motion contributes to your displacement from your birthplace primarily through timing, because the Sun itself has moved considerably in those 30 years. And so, the point where Earth was on the day you were born is no longer anywhere near where Earth returns each year on your birthday. The Sun, you see, is not fixed in place, but rather travels through the Milky Way galaxy at a velocity of roughly 514,000 miles per hour, carrying with it the entire solar system, like a great ship sailing through an ocean of stars. This motion is called the solar apex movement, and the Sun is heading generally toward a point in the constellation Hercules, though this direction shifts over very long timescales as the Sun orbits the galactic center. Over 30 years. This solar motion carries you approximately 135 billion miles from where you started, if we consider only this one component. But we must be careful here, because we are beginning to layer motions upon motions, and the geometry becomes rather more complex than simple addition might suggest. The velocities do not all point in the same direction, you see, and so we cannot merely add them together as though they were numbers on a page. Still, for our gentle approximation, these figures give us a sense of scale that is both humbling and, in its own way, rather peaceful. The galaxy itself is moving, too, participating in a vast cosmic flow that carries the entire Milky Way along with its hundreds of billions of stars and all their attendant worlds. Relative to the cosmic microwave background radiation, which is the faint afterglow of the early universe, and which provides perhaps our best approximation of a universal reference frame. The Milky Way travels at approximately 1.3 million miles per hour. This motion is influenced by the gravitational pull of enormous structures in the nearby universe, including the Great Attractor and the more distant Shapley supercluster, though these names need not concern us overly much at this late hour. What matters is that over 30 years, galactic motion contributes another 340 billion miles or so to your displacement. And when we combine all these motions together, accounting roughly for their varying directions, we arrive at our figure of approximately 49 billion miles. You are that far from the place where you first drew breath, and you traveled there without ever leaving your bed. The precise calculation of such distances is the business of rather specialized institutions, among which the Jet Propulsion Laboratory in Pasadena, California, maintains a particularly useful tool called the Horizons System. This is a computational service that tracks the positions of celestial bodies with extraordinary precision, accounting for all the gravitational perturbations and orbital mechanics that govern the motion of planets, moons, asteroids, and spacecraft. If you wished to know exactly where Earth was at 8:47 in the morning on the 15th of March in 1994, the Horizons System could tell you, expressing the answer in three-dimensional coordinates relative to the solar system barycenter, which is the center of mass around which the Sun and all the planets orbit together. These coordinates are given in astronomical units or kilometers, and they change continuously as Earth pursues its endless ellipse. The Horizons System is freely available to anyone curious enough to query it, and there is something rather lovely about the fact that such precise knowledge of our cosmic whereabouts is simply given away to any person who asks. The matter of coordinates brings us to a practical application of these principles that affects your daily life, though you likely never notice it. which is the global positioning system that guides navigation around the world. The GPS constellation consists of approximately 30 satellites orbiting Earth at an altitude of about 12,500 miles. Each broadcasting precise timing signals that your phone or navigation device uses to triangulate your position. The system depends on clocks of extraordinary accuracy, atomic clocks that measure time by counting the vibrations of cesium atoms. And these clocks must be corrected for effects predicted by Einstein's theories of relativity. This is not a theoretical nicety or an academic concern, but a practical necessity without which the system simply would not function. The relevant physics involves two competing effects. General relativity, which Einstein published in 1915, predicts that clocks run faster in weaker gravitational fields. And since the satellites orbit high above Earth, where gravity is weaker than at the surface, their clocks tick slightly faster than identical clocks on the ground. This effect amounts to a gain of approximately 45 microseconds per day, which sounds vanishingly small, but which would accumulate into significant positioning errors if left uncorrected. Special relativity, which Einstein published a decade earlier in 1905, predicts that moving clocks run slower than stationary ones. And since the satellites are traveling at about 8,700 miles per hour relative to Earth's surface, their clocks lose approximately 7 microseconds per day due to this time dilation. The net effect is a gain of roughly 38 microseconds per day. And the satellite clocks are deliberately set to run slightly slow before launch so that they will keep correct time once in orbit. Without these relativistic corrections, GPS positions would drift by about 6 miles per day, rendering the system useless within hours. Every time you use a map application on your phone, you are relying on physics that Einstein worked out more than a century ago. Sitting in a patent office and thinking about what it would be like to ride alongside a beam of light. This brings us to the deeper question of what we even mean by coordinates, and how we establish a reference frame against which to measure the positions of things. The International Celestial Reference Frame, maintained by the International Astronomical Union, provides our current best answer to this question. The frame is defined not by anything within our solar system or even our galaxy, but by the observed positions of several hundred extragalactic radio sources, primarily quasars, which are the blazingly luminous cores of distant galaxies powered by supermassive black holes. These objects are so far away, billions of light years in most cases, that their apparent positions in the sky change only imperceptibly over human timescales. They provide fixed points against which we can measure the motions of everything else, rather like distant mountains that hikers use to orient themselves, because the mountains do not seem to move even as the hiker walks for miles. The current iteration of this reference frame, called ICRF-3, was adopted in 2019 and includes over 4,000 extragalactic sources, with about 300 of them serving as defining sources whose positions are held fixed by convention. The frame is aligned with the previous version, which was aligned with still earlier frames stretching back decades, so that astronomical observations can be compared consistently over time. Radio telescopes around the world contribute to maintaining the frame through a technique called very long baseline interferometry, which combines signals from widely separated antennas to achieve extraordinarily precise position measurements. The coordinates of your birthplace, if we wish to express them in this frame, would need to account not only for Earth's position relative to the Sun, but also for the Sun's position relative to the galactic center and the galaxy's position relative to those distant quasars. The calculation is not impossible, but it involves layers of transformation that reveal just how provisional any notion of fixed position really is. And here we arrive at a truth that Einstein established in 1905, which is that no absolute rest frame exists anywhere in the universe. This was the foundational insight of special relativity, and it remains one of the more counterintuitive facts about reality that physics has uncovered. We are accustomed to thinking that when we say something is moving, we mean it is moving relative to some fixed background, some stationary stage on which events unfold. But Einstein showed that there is no such background, no privileged vantage point from which all motion can be measured absolutely. Motion is always relative to something else, and no observer can claim to be truly stationary while all others move around them. The surface of the Earth feels like a rest frame to us because we are evolved to treat it as one, but it is no more fundamentally at rest than a passing asteroid or a distant star. The cosmic microwave background radiation provides something close to a universal reference frame, because it fills all of space and can be observed from anywhere. But even this is not an absolute rest frame in the sense that Newton imagined. It is simply a convenient standard, a sea of photons against which we can measure our motion through the universe. The Milky Way moves at 1.3 million miles per hour relative to this radiation, and if we were traveling through space in a different direction or at a different speed, the microwave background would appear slightly warmer in one direction and cooler in another, as Doppler shifts compressed or stretch the wavelengths of the incoming light. Satellite experiments have measured exactly this kind of asymmetry, confirming our motion relative to the ancient light that fills the cosmos. What this means for your birthplace is something gently profound, which is that it exists now not as a fixed point in some absolute coordinate system, but only as a set of relationships. The hospital room or bedroom where you were born has moved relative to the Sun, and the Sun has moved relative to the center of the galaxy, and the galaxy has moved relative to the cosmic microwave background. And none of these motions is more real or more fundamental than the others. Your birthplace is like a word that derives its meaning from other words, which derive their meanings from still other words, all the way down without ever reaching some bedrock of absolute definition. This is not a failure of measurement or a gap in our knowledge, but a feature of how the universe actually works. Space itself provides no fixed grid against which locations can be pinned, and yet the relationships themselves are real and measurable. We can say precisely where Earth was relative to the Sun at the moment you were born, and where the Sun was relative to the galactic center, and where the galaxy was relative to nearby galaxies and the cosmic microwave background. These relationships are encoded in the data archives of observatories around the world, preserved in the careful records of the International Earth Rotation Service and the various space agencies that track our planet's wandering through the cosmos. In this relational sense, your birthplace still exists, defined not as a dot on a universal map, but as a nexus of connections that located you in space and time on that particular day. The coordinates have meaning only in relation to other things, but that relational meaning is enough to make them real. So, if you find yourself wondering, in these quiet moments before sleep, what has become of the place where you were born? You may rest assured that it has not been lost, only transformed. It exists now as a geometric relationship, a set of numbers describing where things were relative to other things on a particular day in a particular year. Those numbers are preserved in ephemeris tables and astronomical databases, waiting for anyone curious enough to look them up. The place itself has been left behind, 49 billion miles distant and receding still. But its coordinates endure, meaningful precisely because they are relationships and not fixed points. This is, perhaps, the kindest way to understand the situation, that home is not a location but a pattern of connections, and patterns can be remembered even when the things they connect have moved on to new configurations. The math is clear on this point, and the math, for all its abstraction, is rather comforting in its precision. Let us consider now what it might truly mean to speak of home, when the very fabric of the universe refuses to stay still, when the coordinates we might write on an envelope have themselves drifted away into the dark between the stars. This is not a sad consideration, though it may seem so at first, but rather an invitation to think more carefully, more gently, about what we mean when we say we want to go home, and whether the place we imagine is a location at all, or something else entirely, something that moves with us wherever we happen to be. In 1927, a Belgian priest and physicist named Georges Lemaitre proposed an idea that would change the way we understand the universe and, consequently, the way we might understand home. Lemaitre suggested that if we could run the expansion of the universe backwards, like rewinding a film, we would find that all the galaxies, all the stars, all the matter and energy that make up everything we know, would converge toward a single point, a single moment of extraordinary density that he called the primeval atom. This was not yet the Big Bang, as we would come to name it, but it was the seed of that idea. The recognition that everything we see around us, everything that makes up what we call here and there, near and far, was once together in a way that defies ordinary imagination. The place where you were born and the most distant galaxy, visible only to our largest telescopes, were once, in a sense, the same place, compressed into a state so dense that the concept of location, as we understand it, had not yet come into being. There was no here and there, no home and away, because there was no space in which those distinctions could exist. This is worth sitting with for a moment, breathing slowly, letting the strangeness of it settle without demanding that it make immediate sense. The universe began, as far as we can tell, from a state in which all locations were one location, and then space itself began to stretch, carrying matter along with it, creating the distances between things, creating the possibility of places, creating the possibility of home. And this stretching has not stopped, has never stopped, continues even now as you listen to these words. As the dark between the galaxies grows quietly larger, cosmologists, those scientists who study the universe on its largest scales, have developed a way of thinking about location that accounts for this continuous expansion, a system called comoving coordinates. In this system, The coordinates themselves are not fixed to some imaginary grid painted on the void, but rather expand along with space, stretching as the universe stretches, so that objects which are simply being carried along by the expansion of space, not moving through space, but moving with it, remain at the same co-moving coordinates even as the physical distance between them grows. It is a bit like imagining two dots drawn on a balloon, each dot staying in its place on the rubber surface, even as the balloon inflates and the dots grow farther apart. In co-moving coordinates, those dots have not moved at all. Their coordinates remain unchanged. And yet, in terms of actual physical distance, the kind you might measure with a very long tape measure if such a thing existed, they are now separated by a greater gap than before. This way of thinking about location helps cosmologists track the history of the universe, and it reveals something curious about our intuitions about place. We tend to think of a location as something fixed, something absolute, a set of coordinates that would remain meaningful regardless of what happened to the rest of the universe. But the universe does not offer us such fixed points. The coordinates we might use to describe where you were born are coordinates that have meaning only in relation to everything else, only as part of a system that is itself in motion, itself expanding, itself changing. The place called home is not a pin stuck in the fabric of reality, but a relationship, a pattern of connections, a particular configuration of matter and energy that identifies itself through its relationships to other configurations, other patterns, other places. In February of 1990, the Voyager 1 spacecraft, having completed its primary mission of surveying the outer planets of our solar system, was instructed to turn its camera back toward the place it had come from, toward the inner solar system, toward the small rocky planet where it had been built and launched more than 12 years earlier, from a distance of approximately 3.7 billion miles. Voyager 1 took a photograph of Earth, a photograph in which our entire world appears as a tiny speck, a pale blue dot, as the astronomer Carl Sagan would later describe it, suspended in a sunbeam against the vast dark of space. Sagan reflected on this image with a kind of gentle melancholy and wonder, noting that everything we have ever known, every human being who has ever lived, every love and loss and moment of joy and sorrow, has taken place on that tiny dot, a mote of dust floating in the cosmic dark. This reflection is not meant to diminish us, or to make us feel small in a way that frightens, but rather to invite a different way of thinking about home, about place, about what it means to belong somewhere. From Voyager 1's perspective, there is no visible distinction between continents, no borders, no cities, no separate nations or peoples, just a single point of light, a single place, a single home shared by everything and everyone we have ever known. The divisions we draw on maps, the boundaries we defend, the distinctions we make between here and there, home and away, all of these become invisible from far enough away, revealing that they were never features of the universe itself, but rather features of our way of thinking about the universe. Useful for some purposes, perhaps necessary for daily life, but not fundamental, not written into the fabric of things. The physicist John Archibald Wheeler, who contributed so much to our understanding of general relativity and the nature of space-time, offered a memorable way of describing how space and matter relate to one another. Space tells matter how to move, he said, and matter tells space how to curve. This elegant formulation captures something essential about the universe as Einstein's theories describe it: the deep entanglement of space and the things that exist within it. The way that location and matter are not separate categories, but aspects of a single unified reality. There is no space waiting empty for matter to be placed into it, and there is no matter floating in some abstract void, but rather space and matter arise together, shape one another, define one another. The place called home is not a container in which your family and your memories and your sense of belonging are stored, but rather the home and the belonging and the memories and the family are all part of a single pattern, a single configuration, a single way of being that cannot be separated into the place on one hand and the meaning on the other. Some astronauts, upon seeing Earth from space for the first time, have described an experience that researchers have come to call the overview effect, a profound shift in awareness, a sudden recognition that the boundaries and conflicts that seem so important from the surface are, from above, invisible, meaningless, arbitrary. Edgar Mitchell, who traveled to the Moon as part of the Apollo 14 mission in 1971, described feeling a sense of overwhelming connection to the universe, a recognition that the molecules in his body and in his spacecraft and in his crewmates had all been formed in ancient stars, that everything was connected, that the idea of being separate from the cosmos was an illusion. Mitchell later recalled that seeing Earth from the Moon produced in him not a sense of homesickness, not a longing for a particular location, but rather a sense of home that expanded to include everything, a home that could not be left because it was not a place but a relationship, a belonging that traveled with him wherever he went. This way of thinking about home as relationship rather than location, as pattern rather than point, has deep roots in human cultures around the world, though it is perhaps most explicitly articulated in the songlines of Aboriginal Australian peoples. For tens of thousands of years, Aboriginal Australians have navigated their continent not by reference to fixed coordinates or written maps, but through sung narratives, stories that describe the journeys of ancestral beings across the landscape, stories in which places are defined by their relationships to other places, by the events that connect them, by the meanings they hold within a larger web of significance. To know where you are, in this way of thinking, is not to know a set of numbers or a position on a grid, but to know where you stand in relation to the stories that connect all places, to know which songs you are inside of, which journeys you are continuing. Home, in the songlines, is not a fixed point, but a relationship, a belonging that is enacted through memory and song and movement, a connection that cannot be taken from you because it is not located in space, but woven through your very being. Perhaps this is what the expanding universe has been trying to teach us all along. If we can bring ourselves to listen, to slow down, to let the strangeness become familiarity, the place you were born no longer exists in the sense that the coordinates have changed. The atoms have scattered. The configuration has dissolved and reformed into something new. But the home you carry with you, the belonging that makes a place meaningful, was never stored in those coordinates, was never dependent on those particular atoms remaining in their particular arrangement. The web of connections that made that place home, the relationships, the memories, the sense of being part of something larger. That web travels with you through the cosmos, stretches with the expansion of space, remains intact even as the physical distances grow. In co-moving coordinates, you have never left home, because you are still at the same point in the expanding fabric, still embedded in the same web of relationships, still part of the same pattern that has been unfolding since the primeval atom began its long, slow blossoming into the universe we know. And in the deepest sense, the sense that the overview effect reveals to those who see Earth from space, there is nowhere else to go, no way to escape to, no exile possible, because the whole cosmos is home, has always been home, will always be home, and we belong to it as completely and as inevitably as we belong to ourselves. The stars that burned long before Earth was formed, the atoms that drifted through space for billions of years before joining together to make the air we breathe and the ground beneath our feet, the light that travels from distant galaxies to reach our eyes, all of this is home. All of this is the same web of connections that makes any place meaningful, any location worth caring about. And when you feel, as we all sometimes do, a longing for the place you used to be, a homesickness for a location that has slipped away into the past, it may help to remember that the home you long for was never really a place, was always a pattern of relationships. And that pattern is still here, still with you, still woven through the fabric of your being. The universe is expanding, carrying all locations away from all other locations, making it impossible, in a strict physical sense, to return to the exact spot where anything once happened. But the web of meaning that made that spot matter, the connections that gave it the name of home, those are not subject to the expansion of space, are not coordinates that can drift away into the dark. They are something else, something that travels with you, something that the universe cannot take from you because it was never located in the universe in that way. It was always located in you, in the pattern of your belonging, in the shape of your attention, in the stories you tell, and the songs you carry, and the memories you hold. And so, as you settle into whatever place you find yourself now, in whatever bed or chair or quiet corner, you can rest assured that you are home, have always been home, will always be home, because home was never a point in space, but a way of being, a way of connecting, a way of belonging that the expanding universe has no power to diminish or destroy. And so we arrive at the final movement of our journey together, a gentle arrival rather than a destination, for in truth, there are no final stopping points in a universe such as ours, only the continuous unfolding of one moment into the next, one position in space giving way to another, the great cosmic drift carrying all things forward in its patient, unhurried way. We have traveled far in our considerations this evening, from the spinning Earth beneath us to the wheeling galaxy that contains our small solar system, from the expansion of space itself to the curious fact that the coordinates of your birth have long since scattered into the void. And now we come to rest. If rest is even possible in a cosmos of such constant motion, with a thought that I hope you will find as comforting as I do, a thought about what you are made of, and where those materials have been, and how very ancient and well-traveled your atoms truly are. You see, every element heavier than hydrogen, which is to say, nearly everything that makes up the solid and liquid and complex matter of your body, was manufactured inside the hearts of stars that lived and died long before our own sun began to burn. This is not poetry, though it sounds rather like poetry, and it is not metaphor, though it has the shape and feel of metaphor. It is simply the quiet truth of nuclear physics, worked out over decades by patient scientists who traced the origins of the elements back to stellar furnaces and cataclysmic explosions. The term for this process, nucleosynthesis, was coined by the British astronomer Fred Hoyle in 1954. A word that sounds rather clinical and technical, but describes something that I think deserves to be called magnificent. The building of atomic nuclei through the slow and violent processes that occur when matter is compressed and heated to temperatures beyond anything we can truly imagine. 3 years after Hoyle gave us that word, a paper was published that remains one of the foundational documents of stellar physics, authored by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle himself, often called simply B²FH after their surnames. And in that paper, they laid out in careful mathematical detail how the elements are synthesized in stars, how hydrogen fuses into helium in the cores of ordinary stars, like our Sun, how helium in turn fuses into carbon and oxygen in the later stages of stellar evolution, and how heavier elements still are forged in the final, desperate burning of massive stars and in the explosive deaths we call supernovae. Margaret Burbidge, I should mention, was a remarkable astronomer who faced considerable obstacles in her career simply because she was a woman working in a field that did not always welcome women. And yet, her contributions to our understanding of the cosmos were essential and lasting. And when you drift off to sleep tonight, you might carry with you the knowledge that her work helped explain why you exist at all. Let us consider, very gently and without any sense of urgency, the calcium in your bones. Calcium is element 20 on the periodic table, with 20 protons in its nucleus, and it is absolutely essential to the structure that holds you upright, the skeleton that gives your body its shape, the teeth that you use to eat, and the countless cellular processes that depend on calcium ions for signaling and function. This calcium was not present at the beginning of the universe, for in the very early cosmos there was only hydrogen and helium and trace amounts of lithium, nothing more. A rather simple inventory of elements that could not possibly have assembled into anything as complex as a bone or a tooth or a living cell. The calcium in your skeleton was forged in the cores of red giant stars, massive, elderly stars in the late stages of their lives, their cores compressed and heated to the point where helium nuclei could fuse together, building heavier elements step by step, carbon becoming oxygen, oxygen becoming neon, neon becoming magnesium, and eventually, through pathways that are wonderfully intricate, calcium emerging as one of the products of these cosmic forges. When those red giants eventually shed their outer layers or collapsed and exploded, the calcium they had manufactured was scattered into space, drifting through the interstellar medium for millions or billions of years, eventually gathering into the cloud of gas and dust that would one day collapse to form our solar system, our planet, and ultimately, in ways that still seem almost miraculous, even when you understand the chemistry, your bones. Now, consider the iron in your blood, the hemoglobin molecules that carry oxygen from your lungs to every cell in your body, each molecule containing iron atoms at its core. Iron that gives blood its characteristic color when it binds to oxygen. Iron is element 26, and it represents something of a turning point in stellar nucleosynthesis. For iron has the most stable nucleus of any element, which means that fusing iron does not release energy the way fusing lighter elements does. Instead, it requires energy. And this fact has profound consequences for massive stars. When a massive star has burned through its available fuel and its core has been converted largely to iron, there is no longer any source of energy to support the star against its own gravity, and the core collapses catastrophically. The outer layers of the star rebounding outward in a supernova explosion of almost incomprehensible violence. It is in these explosions, and in the extreme conditions of the collapsing core, that iron is scattered into space, along with elements heavier than iron that can only be created in such cataclysmic events. The iron in your blood was forged in supernovae, in the deaths of massive stars that lived fast and ended violently. Stars that existed and perished billions of years before our sun was born, their remains mingling with the interstellar medium and eventually finding their way into the cloud of material that became our solar system. This means, if you follow the logic gently to its conclusion, that you are made of star stuff, to borrow a phrase that has been attributed to various scientists and writers over the years, though the sentiment belongs to no one person, but rather to the shared understanding of anyone who has traced the origins of the elements. The atoms in your body are billions of years old. They have been part of many things before they were part of you. They have drifted through the cold depths of space. They have been caught up in the gravitational collapse of forming solar systems. They have been part of the Earth for most of its 4.5 billion year history, cycling through rocks and oceans and atmospheres and living things. And now, for this brief moment in cosmic time, they have come together in the particular arrangement that is you, listening to these words as you settle toward sleep. Speaking of carrying things outward into the cosmos, let me tell you about the Voyager spacecraft. 2 robotic probes launched by NASA in 1977, Voyager 1 and Voyager 2, sent out to explore the outer planets of our solar system and then to continue onward into interstellar space. Both spacecraft carry what are called the Voyager Golden Records, phonograph records made of gold-plated copper, each one containing a selection of sounds and images from Earth, chosen by a committee led by the astronomer Carl Sagan, intended as a kind of message in a bottle for any extraterrestrial intelligence that might someday encounter these tiny ambassadors from our world. The records contain greetings in dozens of human languages, the sounds of wind and rain and surf, the calls of birds and whales, music from various cultures and traditions, from Bach to Chuck Berry to traditional songs from around the globe, and encoded images of life on Earth, of human beings and animals and landscapes, and the DNA molecule. It is a portrait of home, sent outward into the void. And by now, Voyager 1 has traveled over 14 billion miles from Earth, well beyond boundary of the solar wind's influence, officially in interstellar space, though still within the gravitational reach of our Sun, still falling outward at a speed of about 38,000 miles per hour, carrying those sounds of home into the darkness between the stars. The Voyager probes will not reach another star for tens of thousands of years. And even then, they will merely drift past, cold and silent, their power sources long exhausted. But the golden records will survive, preserved by the cold vacuum of space, a message that may never be received by anyone, but that exists nonetheless, carrying with it the sounds of rain falling on Earth, the voices of children saying hello in languages that may no longer be spoken by the time any listener finds them, if any listener ever does. There is something deeply peaceful about this, I think, about the idea that we have sent these small pieces of home outward into the cosmos, not because we expect any return, not because we believe anyone will find them, but simply because it seemed right to do so, to mark our existence, to say we were here. We noticed the universe around us, and we wanted to share what we found beautiful. Consider too that the light from your birth year, the photons that left Earth at the moment you were born, are still traveling outward at the speed of light. And if you were born 30 years ago, then that light is now 30 light years away. If you were born 50 years ago, then 50 light years. A steadily expanding sphere of electromagnetic radiation carrying the news of that moment outward into the galaxy. The light from the hospital room or the house where you were born, if any of it escaped into space, is now incomprehensibly far away, too faint to ever be detected, too diffuse to carry any meaningful information, but present nonetheless. A ghostly trace of that moment still rippling outward through the cosmos, never to return, carrying the fact of your arrival into being to destinations that you will never know. In this sense, every moment of your life is being broadcast outward at the speed of light, an ever-expanding sphere of presence. And though the signal fades and becomes meaningless almost immediately, there is something gently remarkable about the idea that the moment of your birth is still traveling away from where it happened, is still in some sense present in the universe, still moving outward, forever. I mentioned earlier that the universe has no center, and this is worth returning to as we prepare to close our journey together. When the universe began in the event we call the Big Bang, it did not explode outward from a single point in space into a pre-existing emptiness. For there was no pre-existing emptiness. There was no space for the universe to expand into. Rather, space itself came into being with the universe and has been expanding ever since, carrying all the matter and energy within it along for the ride. This means that every point in the universe can legitimately consider itself to be at the center, for the expansion looks the same from every vantage point. Galaxies receding in all directions. The ancient light of the cosmic microwave background arriving from every part of the sky. You are at the center of the observable universe, because the observable universe is defined as everything close enough for light to have reached you since the beginning of time. And that sphere is centered on you by definition, and everyone else, on every other planet, around every other star, in every other galaxy, is also at the center of their own observable universe, equally valid, equally central. The cosmos having no preferred point, no absolute reference frame, no single location that is more central or more important than any other. This is not a diminishment, I think, but rather a kind of cosmic democracy, a gentle reminder that the universe does not arrange itself around any particular observer, that we are all equally present in its vast unfolding, all equally small, all equally significant in our smallness. The place where you were born no longer exists in space. The atoms that made up that place have been rearranged. The Earth has moved. The Sun has moved. The galaxy has moved. The very fabric of space has stretched. But you remain. Here, now, composed of atoms that have traveled for billions of years to assemble into the temporary arrangement that is you. Atoms that will continue their journey long after you have finished with them, cycling back into the Earth and eventually, in the very distant future, perhaps into other stars, other planets, other forms of matter and life that we cannot begin to imagine. And this brings us to the gentle truth that I promised at the beginning. The truth that I hope will settle over you like a soft blanket as you drift towards sleep. We cannot go home again. Not to the physical location in space where we were born, for that location has moved away from us at speeds beyond comprehension and will never return. But home comes with us, written in our atoms, encoded in the very materials of our bodies, the iron and calcium and carbon and oxygen that were forged in ancient stars and have been part of this planet for billions of years and will continue to be part of the cosmos for billions of years more. We carry our cosmic origins within us. We are made of the universe. And in this sense, we are never truly far from home. For home is not a place in space, but a pattern, a process, a temporary gathering of ancient materials into the shape of a person. A consciousness knows, a being capable of wondering about these things while settling into sleep. The cosmos is vast and old and quiet, mostly empty space and silent distances. And within it, you are very small, and that smallness is not a sadness, but simply a fact. Like the fact that water freezes at a certain temperature, or that light travels at a certain speed. And within that smallness, you carry the history of the universe, the deaths of ancient stars, the slow cycling of elements through space and time, and your own small story, which is part of the larger story, which continues to unfold even now, even as your eyes grow heavy, even as your breathing slows, even as you stop following these words and let them wash over you like gentle waves on a distant shore. The Voyager probes drift onward, carrying their golden records into the interstellar dark. The light from your birth continues outward, forever and ever, fading but never quite disappearing, a ripple in the great ocean of space-time. The atoms in your body settle into rest, the same atoms that were once part of stars, that will be part of other things when you are finished with them, that have no permanent home but only an endless journey through a cosmos that is itself in motion, spiraling, drifting, expanding, ancient and ongoing and quietly magnificent. Rest now, knowing that you are where you have always been, in the universe, of the universe, made from the universe, home wherever you are, carrying everything you need within you, your atoms remembering stars even when you do not, your body a small gathering of cosmic dust, temporary and precious, and part of something much larger than any of us can fully comprehend. Sleep well. The universe continues. And you, made of stars, drift gently through it, at peace.